In this video, we're going to take a look at a few power series and determine the radius and interval of convergence, if it does indeed converge. So, first up, we have this power series, and we know that the center of the power series is at x equals 0, and therefore we do know that it converges at least x equals 0. It may not converge at any other number, but it does converge at x equals 0. So, as we did in a previous problem, we are going to use the ratio test, which means we're going to take the limit as n approaches infinity of the absolute value of the ratio of x to the n plus 1 over x of n. And so here we have it. This one is fairly simple to figure out. And so I'm not going to go into a lot of detail about the ratio test here. You guys have done that. You know how to do it. Let's just get right down to the end result. We have the limit as n approaches infinity of the absolute value of n plus 1 times x. So as I said in a previous video, we can bring that x out, and technically that's still absolute value of x, because the reason that we can bring the x out, the variables out, is because as we take the limit as n approaches infinity, x has no effect on that whatsoever. We're only concerned with the terms that have the n in them. So here we have the limit as n approaches infinity of n plus 1. Well, as n gets infinitely large, the limit is approaching infinity. So we have infinity times the absolute value of x is infinity. So what does this mean? This means, according to the ratio test, it diverges. And it diverges for what values? Well, it converges at 0, but that is the only value that it converges at. It then diverges for all x except x equals 0, and therefore the radius of convergence is 0. There is no radius of convergence. So this is an example where you have on the number line, you have your center at A, and it converges at A, and it diverges everywhere else. Next up, here we have a power series. And so we know that it converges at x equals 2. Now, this looks a little bit different than other power series. If we take 4x minus 8 and, just set it equal to 0 as an example. So we get 4x equals 8, or x equals 2, or technically speaking, bringing it back over there, we have x minus 2. And so what we really have in the absolute value is x minus 2, so the center is 2. So let's do the ratio test. And here is the a sub n plus 1 divided by a sub n, or times the reciprocal of it. Simplifying everything, we end up with this. Once again, we can bring out the variables. So I'm going to bring out the constant 2, and I'm going to bring out the term with the variable in it, the 4x minus 8. So we have the 2 times the absolute value of 4x minus 8 times the limit is n over n plus 1. Well, we know that the limit here is going to be equal to 1. So we have 2 times 4x minus 8 times 1 is less than 1 by the ratio test. If we bring the 2, divide the 2 into the other side, we have the absolute value of 4x minus 8 is less than 1/2. And then solving that absolute value inequality, we end up with an interval of convergence. An interval of convergence that looks like this. And the interval of convergence is 15/8, 17/8. And so the center of that interval is 16/8, which of course is 2. We know that our center is at 2, and we already know that is going to converge at 2. And it's actually converging over an interval. All right, so what we need to figure out now that we know what the interval of convergence is we need to determine what is happening at the endpoints. So we have to test the endpoints in the original series. So the endpoints, the first one, 15/8, plug that in for x in our original series and evaluate it. We end up with 2 to the n divided by n times -1/2 to the n, which we can simplify to -1 to the n divided by n. And that converges by the alternating series test. Then we test 17/8. We put 17/8 into the series, we evaluate it, simplify it, and we end up with the basic harmonic 1 over n, which as a harmonic we know is diverges, or if we look at it simply as a p-series, then either way, it is a diverging harmonic p-series. So converges at 15/8, diverges at 17/8. So if we go back, I think I put it up here now. Yeah, we go back here. That means we have to have a less than or equal to here and just a less than here, because the less than or equal to implies that we are including the 15/8 in the interval of convergence. The less than symbol means we are not including the 17/8 because it diverges at 17/8. It converges at 15/8. All right, so this is a few different examples of different situations. All right, let's use green. So this one, it's simpler to see. We have x minus 3. So a is equal to 3, and we know that it converges at 3. Doing the ratio test, we get down to this part right here. And now we can remove the x minus 3. And so we have the absolute value of x minus 3 times the limit as n approaches infinity of n over n plus 1, which once again is 1. So we have the absolute value of x minus 3 times 1, and that by the ratio test has to be less than 1 to converge. And so we have x with our radius of convergence in this form is 1. Our interval of convergence then is going to be, the interval of convergence is from 2 to 4. So the center was at 3, and that makes sense. 3 is the center, so we have on a number line the center at 2. There's my a value. 3. And then we have an interval from 4 to 2. And so what we want to do now is determine, is 2 in the end, we want to, our interval is going from here to here. Do we include the 2? Do we include the 4? Is it an open circle or closed circles? So we take the endpoints, take x equals 2, plug it into our series. We end up with -1 to the n over n, which is once again converging by the alternating series test. And plugging x equals 4 in to our series, we once again get the diverging harmonic. And so x equals 4 diverges, so it is less than, and at 2, it is converging, so it is less than or equal to. And so if we were to do this on this number line, we would have a closed circle at 2 because we're including that point, and an open circle at 4. Or if you like the brackets, this would be a bracket, and this would be a paren. So that is a slightly different problem as far as the outcomes go. Next one up, x equals -1/2 is the center, which of course we can get from this. So again, you can simply say, okay, well, 2x plus 1, let's just set that, equal to 0. Subtract the 1, you get 2x equals -1. x equals negative 1/2. That's one way that you can find the center. It's just like if you have a simple one like x plus 1, you set that equal to 0, you get x equals negative 1. That's the center. Okay, get rid of all that. So we're going to do the ratio test on this again. And we end up with this. And as always, I'm going to pull out the variable terms and take the limit of the terms that have the n. And so we have the limit as n approaches infinity of n plus 1, which of course is approaching infinity. So 2x, the absolute value of 2x plus 1 times infinity is infinity, which is not less than 1. It's greater than 1, so that means it diverges by the ratio test. So once again, it diverges for all values of x except the center at x equals negative 1/2. Therefore, the radius of convergence is 0. The interval of convergence does not exist. It is 0 and converges at x equals negative 1/2. In this power series, we have x to the 2n. So the center is at 0. And so we know that it converges at 0. Doing the ratio test, this is a cute one to do the ratio test on, so make sure that you understand everything that is going on here with the ratio test. It can be a little bit involved. And if you have any questions, you can always ask me, and I can go over it in more detail. But as always, we get down to this point. And so I'm going to remove the x squared and the 4, just leaving in the terms with the n's. So we have 1/4 times the absolute value of x squared times the limit as n approaches infinity, which then this limit is going to be equal to 0. So we have 1/4. I don't need to write that down. It's right here. So we have 1/4 times the absolute value of x squared times 0, which of course is equal to 0. Well, 0 is less than 1. So by the ratio test, we want this to be less than 1. Well, when is this less than 1? 0 is always less than 1. If 0 is always less than 1, no matter what the value of x is. This is what this is trying to say. This is the part that sometimes gets a little confusing. All right, whenever you end up with a 0, well, 0 is always less than 1. No matter what the value of x is, this is always going to converge. So it converges for all values of x, not just the center value, but for all values of x. And therefore, the interval of convergence, the radius of convergence is infinity, and the interval of convergence is from negative infinity to positive infinity, because it doesn't matter what the x value is. It's always going to converge for all values of x. So let me just kind of summarize two different types of problem we have here. So whenever we end up with infinity, so when we're doing the ratio test, if we end up with infinity, infinity is always greater than 1, and therefore it diverges always. Always. So that means that the only place where it converges is at A. It converges at A. The radius of convergence is 0. The interval of convergence is 0. But what happens if we end up with a 0? 0 is less than 1 always. So it converges always. Doesn't matter what the value of x is. It's always going to converge. So therefore, our interval of convergence is from negative infinity to positive infinity. And so the first one, our interval of convergence is 0. The second one, it's negative infinity to infinity. Here's another one where it is centered at 0. And so doing the ratio test, we end up with the limit as n approaches infinity of x squared over negative 3. And of course, that negative 3, the absolute value of negative 3, when we pull it out, we can just make it 3. And again, sometimes I forget to put the absolute value around there. And so the limit of 1 is 1. So we have 1/3 the absolute value of x squared times 1. And so that has to be less than 1. And the reason what I'm saying is the limit of 1 is 1. The limit of a constant is a constant. And so if we have let's take this and solve it for x. When we solve that for x, multiplying both sides by 3, taking the square root of both sides, we end up with x is less than plus or minus 3, so our interval convergence would look like this. And right now I'm using just less than symbols because I don't know if we're including the endpoints. So we now have to test the endpoints. So we're going to test the first endpoint, which is negative radical 3. And we plug that into our series, and we end up with negative 1 to the n, which is divergent by the divergence test. Okay. And it diverges. Then we're going to test the other endpoint, which is radical 3. Plugging that into our series, we end up with negative 1 to the n, and it is also divergent by the divergence test. Therefore, at both endpoints, it is divergent, and so our interval of convergence looks like this. And I believe this is the last one. And we're going to actually use the root test for this one, just to change things up a little bit. And the reason that we're going to use the root test for this is because we have the x minus 6 raised to the nth power and n raised to the nth power. So that makes it somewhat convenient. And so we take the x minus 6 to the n all over n to the n. And the one thing that, I need to mention in this is that n is not supposed to be there. I don't remember why it ended up there, but it's not supposed to be there. And so we have x minus 6 to the n over n to the n. And we raise that all to the 1 over n power. This is 1 over n power. And so we end up with the absolute value of simply x minus 6 over n. And so once again, we bring out the part with the variable in it, absolute value of x minus 6 times the limit as n approaches infinity of the absolute value of 1 over n. And that, of course, is going to approach 0. So we have the absolute value of x minus 6 times 0, which is 0. 0 is always less than 1, and so therefore it converges for all values of x. Converges for all values of x because this is always true, and our interval of convergence is from negative infinity to positive infinity. Well, there's a bunch of examples of determining convergence, the radius of convergence, the interval of convergence for power series.